This is video 2 for section 6.6, and we're picking things up on number 11. Number 11 talks about an airplane flying at looks like a constant altitude of 7 miles per hour and passes over a radar station when the plane is 10 miles out. So the plane is obviously moving when it's 10 miles out, so that would be the way I've set it up. Actually, the book too. They're talking about the time when x equals 10 miles. Again, that's not a constant. Oh, hold on. Changing it up here. It says when the plane is 10 miles from the antenna, s equals 10. So they want s to be that straight line distance to the plane and not the horizontal distance. Alright, helps to read. So s equals 10. The radar detects the distance s is changing at a rate of 300 miles per hour. So we need to label that somehow. And it's talking about s as a rate of change, or as s is changing, and it says the rate of change. So s is changing ds with respect to time of 300 miles per hour. And we need to note, and it's good to always start paying attention to, s is getting bigger, so its rate of change should be positive, so positive 300. If s was shrinking, we would have said negative 300. It says, what is the speed of the airplane at that moment? Okay. So the airplane is flying here. So x is increasing at a certain amount, and that's what they want us to measure. They want to know what is dx dt. Alright, so I think I've labeled everything I know. The 7 miles doesn't change. S happens to be 10 right now, but it's going to be changing. So we're not going to fill that in with a number. And they want to know about x. So I need to find a way to relate x and s, and that would seem to be the Pythagorean theorem. So I know that s squared equals 7 squared plus x squared. S squared equals 49 plus x squared. But I don't want just the current state of things. I want to know how x is changing. So if I want to know about dx dt, and I know ds dt, then the derivative with respect to time seems appropriate. So taking the derivative of s squared gives me 2s ds dt equals the derivative of 49 is 0, because 49 isn't changing, so it would make sense that its rate of change is nothing. And the derivative of 2x is 2x dx dt. So let's look at what I need to solve. I'm looking for dx dt, so I need everything else. I know s is 10, I know ds dt is 300. I don't know x, but please remember we have the Pythagorean theorem to relate these three sides. So if I know this is 7 and this is 10, then I should be able to find x by simply doing 100 s squared. S squared is 100 equals 7 squared plus x squared. So that's 49. I subtract 49, I get 51 equals x squared. So x would appear to equal the square root of 51. So now I plug in everything I know. 2, s is 10, ds dt is 300, equals 2 times the square root of 51 dx dt. So dx dt equals 20 times 300 over 2 times the square root of 51. The 2 and the 20 reduced to be 10. So I get 3,000 over the square root of 51, and that would be in miles per hour dx dt. That's what dx dt equals. So let's go to a decimal just so we can have that answer too. So 3,000 divided by the square root of 51, which I'm doing on my calculator, is 420-ish. So that appears to be 420.084 miles per hour. Okay, so on to number 12. Number 12 says we're filling a trough with water. The trough is 15 feet long, so that's not changing. 4 feet across the top, so I've drawn a little cross section here, so this is looking straight at it. So 4 feet across, 3 feet tall. Water is running into the trough at a rate of 2.5, so let's write this down, 2.5 cubic feet per minute. So what is changing at 2.5 cubic feet per minute? And the answer to that would be that's how fast the volume is increasing. So the water is being poured into, and so the volume is getting bigger. So we're going to say dV dt is equal to a positive 2.5 cubic feet per minute. How fast is the water level rising when it is 2.5, or I'm sorry, when it is 2 feet deep? So they're asking about height of the water, which is currently labeled as 2. So let's think about this as the height right here in my little drawing. And so they're looking for dH dt. Okay, so once again, if I know I know information about the rate of change of volume and I'm looking for the rate of change of height, then I need to start this process by writing a volume equation that includes height. So the volume of water, no matter what height the water's at, would simply be, so if the water level is, at this level, it's still going to be a triangular prism, okay, because it's conforming to the shape of the trough. So no matter what height you're talking about a triangular prism. So the area of which would be area equals, oops, I'm writing a very bad equation here. So base times height, so the area of the base is going to be 1/2 base, which I guess we can leave as b, times height. And by height we again mean the height of the water. So that area times the length of the trough, but that's just 15 feet. That's not changing. So we can just plug in the 15. Okay, so notice if I were to take the derivative right now, I'd have a dV dt, which is fine. I'd get a dH dt, which is fine. But I'd also get a dB dt. And I don't have any information on dB dt. So before I take a derivative, my goal now has to shift. I have to find a way to change b into a different variable, like h. Alright, and the answer to how we're going to do that, I'm going to blow up this picture a little bit so I can draw in it. The answer to how we do this is realizing that no matter what water level we're at, so maybe the water level is here, maybe it's here, maybe it goes all the way to the top, okay? But no matter how we do it, all of these triangles are going to be similar triangles because they all share this bottom angle. That triangle, this triangle, the whole trough all has this as its bottom angle. And the water level is going to be parallel. So we know that that is congruent to that, is congruent to this, and then we have these all congruent over here. So again, no matter what water level we're at, we have similar triangles. And the nice thing about similar triangles is the ratio of their pieces is also going to be proportional. So what that means is they gave us the big triangle. And they told us that the length across was 4 and the height was 3. So I can write a statement that says that the radius, well, let's see, let's call it base, because that's what we called it up in our equation. The base to the height is of the ratio 4 to 3. So that ratio is going to hold true for all these similar triangles, no matter what level the water's at. So I can easily, again, I want to know about dHdt, so I need h in my problem. So I'm going to rewrite this to say base equals 4/3 of a height. And now, when I plug in 4/3 of height in for base, all I've got is height and volume in my equation. So volume equals 1/2 base, which is 4/3 height times 15. So volume equals, let's see here, the 2, we'll reduce this to 2. The 3 will reduce the 15 to 5. And I'm left with no more denominators. I'm left with 10h squared. And so dV dt I can now take, giving me 20h, 2 came down, changed it to 1, don't change the inside, times dH dt. Plugging in what I know, and I'm making a bit of a mess, excuse me. dV dt is 2.5, 20. Height, they told us that this snapshot in time that we're talking about, the height is 2. So h is 2, and dH dt we're looking for. So dH dt appears to be 2.5 divided by 40, which, let's go ahead and grab our calculator. 2.5 divided by 40 is going to be a rate of change of the height of 0.0625. And they answered what units is height is a one-dimensional, so it's going to be feet per minute. So the water level is going up, not very fast, but it is going up. All right, I'm going to go ahead and stop this video, and we'll pick it up on number 13.